Hello everybody, I'm Édouard Bonnet. I'll talk about the inapproximability of the diameter problem. So just to be on the same page, the diameter problem, you're given a graph and you want to find the longest distance between a pair of vertices in your graph, so the longest, shortest path between two vertices. In weighted graphs, there is nothing known better than solving all pair shortest paths, so computing all the distances, and that takes roughly cubic time. If you assume that you don't have edge weights, there is a way to solve it essentially in matrix multiplication time. And the focus of this talk will be sparse graphs, where the number of vertices, n, is roughly the same as the number of edges. So the number of edges is n times polylog in n. Also, we'll be considering the time versus approximation trade-off, and this will be clear on this picture. So this is the current picture for the directed unweighted diameter, so when you can have arcs instead of edges. So one axis is the approximation factor, the other axis is the exponent of the runtime. Algorithms are in blue, lower bounds in red. For instance, this blue dot here is 2 approximation that takes linear time. And to get that, you just run 1 BFS from an arbitrary vertex and you output the largest distance. This one here is now 1 approximation, so an exact algorithm that takes quadratic time. So for that, you run n BFS from every vertex of your graph, and you output the largest distance, which will be actually the diameter. There is this non-trivial result in between, which is a series of work here. So it says that you can 1.5 approximate in times roughly n to the 1.5, and you see also a lot of lower bounds, those red dots, actually infinitely many of them. So it started with this one. We'll show a proof of that. It's a very elegant proof. Lee in 2020 got the second one here, and very recently, again, Lee and independently Dalurford and Wien got this staircase, infinite staircase of lower bounds that was complemented by Lee, not by an algorithm, but by an impossibility of getting a lower bound. So under another complexity assumption, the fact that SETH-hardness is not obtainable. Now that's what was known for the undirected unweighted diameter. You see, in addition to the 3 algorithms that we saw on the previous slide, there is a series of upper bounds here. And what has disappeared is the staircase of lower bound. The result in our paper is to provide this third red dot, so this third lower bound on this assumed staircase of lower bound that would complement at this point the impossibility by Lee, but maybe at some point that would contrast with an algorithm. All the lower bounds on the previous slide were under the strong exponential time hypothesis, which says that for every k there is an epsilon such that you cannot solve ksat faster than 2 minus epsilon to the n. An informal statement is that you cannot solve SAT without specifying the length of the clauses in time better than 2 to the n. So you cannot solve it in 1.99 to the n. So it's a conjecture that appeared in the same paper where the exponential time hypothesis was introduced, which is a weaker statement. So you have this chain of implication, SETH implies ETH, and they are both implying P different from NP. So it seems that they will be more suitable to rule out running time for problems that are NP-hard, but it happens that you can also use them, as we'll see here, for problems that are polytime solvable. To us, the first time this was done was in 2005, and then starting 2014, maybe even a bit earlier than that, there was a flurry of papers showing lower bounds for problems in P using this assumption on an NP-hard problem. Let's see how this can work. So we want to design a reduction from SAT to a problem in P. We'll take the example of two orthogonal vectors for the problem, which is polytime solvable. And this problem is the following. You want to find two orthogonal vectors being given a set of vectors, and we'll work with 0, 1 vectors. So basically what we want is two vectors, and at every position there is at least 1 0 at the corresponding index. So not only we have more time to build our new instance of two orthogonal vectors, but we can build larger instance of what we could think with a usual polytime reduction. So here we're using a stronger assumption that SAT cannot be solved faster than 2 to the n. So potentially we can take 1.99 to the n to build the new instance. And also the new instance can and probably should have exponential size. So here, if we want to say that the brute force is essentially best for two orthogonal vectors where, well, the brute force will take quadratic time, we can build an instance with that many vectors, 2 to the n over 2. So again, this makes sense. If you could now solve two orthogonal vectors in subquadratic time, you would get overall, running this reduction, something solving SAT faster than 2 to the n. So we'll actually see the reduction. It's quite neat. So what you do, you take your variables, you partition them arbitrarily. Here the red variables, the blue variables. And now the problem will be to find the partial assignments, an assignment of the red variables, an assignment of the blue variables, satisfying everything. So it's obviously equivalent, but it's a convenient way of seeing it because now we will have this compression that we'll only express assignments over n over 2 variables. So now what you do, you reserve two indices to encode if you're from the red set or the blue set. So this would mean that A1 corresponds to the red variable. So here I will build some vectors, and you have one index per clause, and at index corresponding to clause Cj, for instance, you put a 1 if the corresponding partial assignment does not satisfy C1, and you put a 0 if it satisfies. So you get vectors like that, and you see that if you want to find two orthogonal vectors that have a 0 at every index, you'll have to pick one red vector, one blue vector corresponding to partial assignments. So overall it corresponds to total assignments, and they will have combined to satisfy all the clauses, so it's exactly what you want. So let's be a bit more specific. So we started with a SAT instance on n variables and n clauses, and we created 2 to the n over 2 plus 1 vectors, and the number of indices that we needed, the dimension of the vectors, was basically the number of clauses plus 2. So we could actually also include d in the running time that is unlikely to happen for orthogonal vectors, otherwise we would break SETH. But actually something more useful to us is to realize that even when the dimension is comparatively low compared to the number of vectors, so in that case it would be polylogarithmic, then this lower bound that you cannot solve two orthogonal vectors in subquadratic time holds. And more generally, the same trick, partitioning the variables into k batches instead of 2, would give the following lower bound for k orthogonal vectors that you cannot get below the brute force approach that would give n to the k. And it turns out that two orthogonal vectors was used as a starting point to show the first lower bound for the approximately of diameter. So this is a reduction by Roditi and Wasilska-Williams, which is very elegant. We'll present it on this slide. So you start with your input of two orthogonal vectors, you make two copies of the vectors, so those vertices correspond to the vectors, same as those vertices in B, and a set in red here with one vertex per index. Then you make vertex A universal to copy A and the indices, and vertex B universal to copy B and the indices. So far, every pair except a pair of the form A and B are at distance at most 2. Now you introduce the interesting edges. So basically you put an edge between a vector AI and an index j if AI of j is 1. Okay, so you get an instance. So now you notice that if you have two vectors that are at distance 2, it means that there is a path with two edges that has to go through the indices. So at one index, they have both a 1, meaning that neither of them has 0, so they are not orthogonal, which means that if all the pairs are non-orthogonal, then all the pairs AB are at distance 2 and the diameter of all is 2. And if there is one pair that is orthogonal, then it realizes diameter 3. So you see that you cannot distinguish from 2 to 3, and it's a linear reduction from two orthogonal vectors. So it gives, if you remember the lower bound, that you cannot get something subquadratic if you want to distinguish between diameter 2 and diameter 3. Let's now state our results. So in the same setting as sparse, undirected, unweighted diameter, we show that getting better than 7/4 approximation essentially requires time n⁴ under the SETH. So this 7/4 means that we'll show the hardness of distinguishing between diameter at most 4 and diameter at least 7. And this running time that we want to match here means that we'll reduce from 4 orthogonal vectors, where we're allowed to produce instances of cubic size, so cubically many vertices, and up to logarithmic factors, cubically many edges. So it's the same opening step as we saw in the previous slide for 2 versus 3 diameter, starting from 2 orthogonal vectors. And it's also the same in the result by Lee, which we didn't present, showing the hardness of 3 versus 5 diameter starting from 3 orthogonal vectors. We first present the reduction with edge weights. We'll remove the weights later, but it will be simpler that way. So the vertex set is partitioned into 4 sets, T, C, P, and I. Let's start describing T. So T stands for tripoles. So for each tripole of distinct vectors in the 4 orthogonal vectors instance, we'll have one vertex corresponding to that tripole. C stands for couples. So vertices within C, they have 5 fields. The first 2 are vectors, and the last 3 are indices. For this vertex A, B, I, J, K to exist in C, A should be 1 at position I, J, K, and B should be 1 at least 2 of 3 among the indices I, J, K. P stands for pairs. So now the order of the 2 vectors is not important. We denote them with a set, and both D and E should take value 1 at index I, J, K for this vertex to exist within P. Finally, I. In I, vertices have 5 fields that are all indices. I denote the first 2 P1, P2, and the last 3 I, J, K for a reason that will become apparent when we add the remaining edges. Let's now describe the edges. So we'll first make I a clique, and in C we'll link every pair of vertices agreeing on the first 2 coordinates, so meaning the 2 fields corresponding to a vector. And now we'll add edges from T to C, from C to P, P to I, and I to T. So let's start with the interaction between T and C. So we'll add an edge between ABC and ABIJK, so they need to match on the first 2 coordinates. If there is an index among IJK where both C and B take value 1. From C to P, we'll put an edge between ABIJK and DEIJK simply when A appears in the set, so is either D or E. From T to I, we'll have edges with a weight of 3. And this edge between ABC and P1, P2, IJK will exist if A, B, and C takes value 1 on both P1 and P2. Finally, there will be an edge between P1, P2, IJK, and DEIJK, so the 3 last indices have to match. If either D takes value 1 on P1 and E on P2, or the opposite, D takes value 1 on P2 and E on P1. So that's it for the construction. One can check that the number of vertices and the number of edges is up to logarithmic factors cubic. Remember that the number of different indices is polylogarithmic. So now we want to check that the reduction is correct and indeed creates a gap between diameter at most 4 and diameter at least 7. So let's start by showing that if there is no orthogonal quadruple in the 4 orthogonal vectors instance, then the diameter of the graph we just constructed is at most 4. Because of this set I, which is a clique, there are many pairs of vertices that are automatically at distance 4. Actually, every pair which is not of the form TT, TC, TP, or CC has automatically a path of length at most 4. So one can assume without loss of generality that every vertex has at least one neighbor in an adjacent set. So for instance, every vertex in P has at least one neighbor in I. So now if I take a pair of vertices, one in P, one in C, from the vertex in C I have a path of length 2 towards I. From the vertex of P I have a path of length 1. And from the two endpoints, because this is a clique, I can finish the path of length 4. So for every other pair of vertices that do not fall in this category, you will find a path of length 4, and this will not depend on the particular instance of 4 orthogonal vectors. So let's see why there is a path of length at most 4 between any pair of vertices that are both in T. So we want to go from any vertex ABC of T to any vertex DEF also in T. So I claim that there is a path that goes ABC, ABIJK, ADIJK, DEIJK, DEF. So I need to tell you how I chose the indices IJK. Because there is no orthogonal quadruple, whenever you give me 4 vectors, let's say A, B, C, and D, there is at least one index where all those 4 vectors take value 1. So I can define IJK in the following way. And now I claim that all the vertices and the edges that were on my path of length 4 actually exist. So for that, you need to check that A and D appears in I, J, and K. That's the case. That B appears in 2 of IJK, namely I and J. That E also appears in at least 2, which is the case, J and K. And that C appears in 1 together with B, which is the case with I, and F appears with 1 together with E, which is the case with K. So this path indeed exists, and if I want to tweak it a little bit to go from T to C or from C to C, I would need to start or to end with taking an edge internal to C instead of taking the edge from C to T. But this edge between AB, I prime, J prime, K prime, and AB, I, J, K exists by construction. Same, an edge between D, I, J, K and D, any triple of indices exists. So that settles those three cases. Now we need to deal with a pair, one vertex in T, one vertex in P. And here it's not clear how to find a path of length 4 within T, C, and P. So that's why we have I. So we'll take one edge of weight 3 and one edge of weight 1. And I claim again that there is a path that goes ABC, P1, P2, IJK, D, IJK. So how do I choose P1 and P2? So IJK are imposed by the choice of the vertex in P. So P1 is the index where A, B, C, D take value 1, and P2 where A, B, C, E take value 1. That way this edge indeed exists. A, B, C all take value 1 at P1 and P2. And that edge also exists because D takes value 1 at P1 and E takes value 1 at P2. So we're in this case here. Now conversely, we will show that if there is an orthogonal quadruple ABCD, then the diameter of the graph is at least 7. More precisely, the distance between vertex ABC and vertex DCB is at least 7. The first observation is that a path of length at most 6 between ABC and DCB cannot include an edge of I. This is because the distance between set T and set I is 3, either by going directly with a blue edge or 3 edges of weight 1. So we can already forget about the edges of the clique here. And actually any path of length at most 6 using a blue edge would contradict this orthogonality. Why? I mean, if you go back and forth T, I, and then back to T, then index P1 and P2 both contradict the orthogonality of ABCD. A bit more interestingly, if you go T, C, P, I, and then back to T, that would also contradict the orthogonality of ABCD in a more subtle way. So let's say you start from ABC. In P, you will have a vertex of the form A something IJK. And then going to I, one of P1 or P2 will be an index where A is taking value 1. And now you want to go back to DCB from this vertex, but all D, C, and B should take value 1 at this corresponding P1 or P2. And again, we have one of P1 or P2 where A, B, C, D takes value 1, which is not possible. There could still be a path going T, C, P, I, and then back P, C, T, but it won't make a difference with cases staying within T, union C, union P. For all these cases, one can observe that there will be along the path 2 vertices of the form ABIJK and DCIJK for some triple of indices IJK. And now we reach a contradiction because by the existence of those 2 vertices in C, it means that A and D take value 1 at IJK, while B and C take value 1 at least 2 of those 3 indices. So they intersect at least one index. So there is one index where A, B, C, and D take value 1, contradicting the orthogonality of A, B, C, and D. Let's conclude by briefly showing the construction without edge weights. So we had only edge weights between T and I. So what we do is that we duplicate T into T, T prime, T prime prime, so that we can subdivide this weight, those weight 3 edges that we had between T and I into 3 edges of weight 1. We make C adjacent to T and T prime the same way C was adjacent to T. And now because we introduced more vertices, there are some pairs that should be at distance 4, but are not necessarily. So we add another set I prime, which is together with I a clique, that settles those particular pairs. And the rest of the proof is using more or less the same arguments as we saw previously, and paths going through I union I prime. So I thank you a lot for watching, and I encourage you, if you have questions, to come to the live talk and the Q&A session. So thank you again. Bye.